public lectures to welcome you to this first in a series of 4 lectures on the vital centers of human decision-making. I think we all recognize that this is an anomalistic age, an age peculiarly of decision and of indecision, a time at which, perhaps more than ever before, man is capable of making, I see that I cannot be heard. Is this, does somebody know if this is on or is supposed to be on? It's not. Well, is there somebody who knows something about this, perhaps? Professor Pickering says try the switch. But there is no switch. Can I be heard now? That's nice. Well, the point that I was trying to make by way of introduction is, I think, an obvious point, that more than ever before, man is capable today of making decisive changes in the human condition, and yet perhaps also more than ever before, man tends to be uncertain about what the consequences of these changes will be. And there is withal a mystique, an air of mystery about the centers in which crucial decisions are being made. It is our hope that by focusing in this series on 3 of the vital centers of human decision-making, that conceivably we can help clear up something of the mystery by focusing on those places in which decisions are being made concerning outer space, concerning inner space, the psyche, concerning political space, that is to say, specifically presidential decisions, and then finally by reflecting on the philosophic and even spiritual implications of the decisions being made in these centers, that we can contribute something to a broader and deeper understanding of complex forces which are molding our way of life. And it's our honor tonight to have with us, to inaugurate our series, a man who has made signal contributions to man's great venture in outer space, and who in a real sense personifies the cosmic aspirations and attainments which are, I think, among the most striking features of the present epoch. To introduce our speaker to you, I should like to present Professor Gordon J.F. McDonald, Professor of Geophysics at UCLA and Associate Director of the Institute of Geophysics. Professor McDonald. It's my job to introduce Professor Pickering. In some ways, I think it's quite unnecessary, particularly to those avid readers of Time magazine. However, I might mention a few things that Dr. Pickering is involved in that come rather closely to those of us in the universities. Dr. Pickering, as you are aware, has made it his business to run the Jet Propulsion Lab of the California Institute of Technology for the past 9 years. During the last 5 of these years, he has been concerned with the scientific exploration of space. In this, he has had to work with scientists and engineers in his own laboratory, but he has also faced perhaps an even more difficult task, that of working with scientists in the universities who are partners in in this scientific exploration. In this job, Dr. Pickering has done such a magnificent job that the scientists in the universities have been able to accomplish far more than many of them initially expected. One other point that we might bring up is, of course, the latest success of the Jet Propulsion Lab, the launching of the Mariner 2 vehicle, spacecraft, that has provided an almost unbelievable wealth of information. The first flash has gone out of this information, but it'll be many years before the data are properly digested. It is Dr. Pickering's laboratory that has made that wonderful experiment possible. Dr. Pickering has chosen as his topic for tonight, Man at the Threshold of Space.
Thank you very much. President McDonald, Mr. Poet, ladies and gentlemen. For some 50 years or more, some writers and thinkers have been concerned about the consequences for humanity of allowing science to run roughshod over all facets of life. From Jules Verne to Orwell, they have painted a grim picture of life under a scientific dictatorship. As one reads these books, it's surprising to realize how many of their prophecies have already come to pass, and consequently to wonder if we are inevitably heading for one of these dreary, negative utopias. Today, we are on the threshold of space. Science and engineering together have solved the problem of permitting man to step off his little planet into the emptiness of the solar system. Does this dramatic event presage the beginning of a golden era for the submergence of all human values? First, let us consider exactly what is meant by saying we are at the threshold of space. Of course, we're all familiar with the feats of the astronauts in the race to the moon, but let's look behind these spectacular headlines and review exactly what is going on in the space programs of this country and the Soviet Union. It's now about 5.5 years since the Soviets startled the world by announcing that they had a satellite in orbit. October the 4th, 1957, the first Sputnik. I'm sure that many of you remember the excitement produced by that first space event. The Soviets had arranged to have a shortwave transmitter on the Sputnik so that people all over the world with reasonably good shortwave receivers could listen to the satellite and assure themselves that it was indeed in orbit. Furthermore, the radio signals reported instrument readings from space so that scientific data were being collected for the first time from far above the surface of the Earth. I will not concern myself here with the political repercussions of this event, but I do want to note two important thought processes which I think this first Sputnik generated. First, it showed conclusively that the Earth is round. And secondly, that the Earth is not very big. Now, neither of these ideas is new, of course, but the satellite demonstrated both of these ideas in a very spectacular manner, and I suspect it brought home to people all over the world these scientific facts. As we all know, at the end of January 1958, the United States launched its first satellite, very much smaller than the Soviet satellite, to be sure, but nevertheless a good scientific satellite, and with this launching the space race was on. How much the program has grown can be illustrated by the budget of the National Aeronautics and Space Administration. Starting from almost zero in 1958, it has grown to 3.75 billion in the current fiscal year, and the NASA has asked for 5.5 billion in the next fiscal year. There is every expectation that Congress will grant this request. The space program has spent a tremendous amount of money with the support and approval of the Congress, and I expect the Soviets have spent comparable amounts of money. What has come about as a result of these expenditures? First, let us consider the close-in Earth satellites. During these 5.5 years, the size of Earth satellites has grown from a few pounds to a few tons. Satellites have carried scientific instruments of a wide variety. They've carried biological specimens. They've carried a man into orbit. The orbits which have been used range from orbits near the equator to orbits over the poles, to orbits which are circular and just above the Earth's atmosphere, and orbits which reach far out into space between the Earth and the Moon. As a result of these satellite firings, there has been gathered a great deal of scientific information. We have a wealth of knowledge now about the extreme upper reaches of the Earth's atmosphere, of the environment in space in the near vicinity of the Earth, of the appearance of the Earth from a satellite looking down on the Earth, and indeed even of such things as the exact shape of the Earth, because it turns out that the path of a satellite in orbit will give us a very precise measure of the exact gravitational configuration of the Earth. The first U.S. satellites discovered the Van Allen radiation belts, which surround the Earth and which are of considerable interest in a practical sense because of the radiation hazard which they portend for space travelers and explorers who may tarry too long in these regions. The satellites have also produced practical results. For example, in the general area of applications, we have such things as the Echo satellite, the Telstar satellite, and the TIROS satellite. The first two demonstrated the capability of satellites to be used for communications purposes. There's no doubt whatever that in the future there will be a growing interest in satellite communications. In fact, satellites will probably be the only economically feasible answer to the growing load of transoceanic telephone communications. TIROS first showed what could be done by looking down at the Earth from a satellite. It gave the meteorologists a great deal of new information about weather and cloud formations. Undoubtedly, TIROS is only the first in a series of meteorological satellite developments which should lead not only to a better understanding of weather phenomena, but also to more accurate weather forecasting, and we need it here in Southern California. The next satellite in this series will be called Nimbus, and will be flown next year. Another area of results of the satellite flights is the human area. Human area. Here I think it's only necessary to mention that both this country and the Soviets have successfully orbited astronauts, recovered them safely from orbit, and clearly this adventure is of tremendous human interest to people all over the world. Another area of space exploration is the area of deep space exploration, to the Moon and to the planets. Both the Soviets and the U.S. have conducted experiments in deep space. The Soviets have successfully launched 4 space probes towards the Moon, Lunik 1, 2, 3, and 4, with varying success. Lunik 3 was probably the most interesting because this succeeded in taking some photographs of the backside of the Moon. 4 photographs to be sure, but nevertheless showing a portion of the Moon never before seen by human eye. The U.S. has launched 3 spacecraft towards the Moon, ranges 3, 4, and 5, of which range of 4 actually landed on the Moon, but none of the 3 accomplished their scientific missions. In the planetary area, the United States successfully launched Mariner 2 towards the planet Venus last August. Data were received during the entire journey to Venus, and also scientific observations were made of the planet as the spacecraft passed nearby at a distance of about 20,000 miles. At the present time, the Soviets have a spacecraft, which they call the Mars 1 space probe, on the way to Mars. It is expected to pass the planet in the middle of June. The Soviet reports, the last I had seen at least, say that it is still working satisfactorily. These deep space experiments have given us much scientific information about the environment of deep space and about such things as the solar plasma, or the solar wind, as it's sometimes called, the magnetic fields, and the micrometeorites to be encountered in journeys through space. With Mariner 2, we also began the exploration of another planet by instruments placed near the planet. There is no doubt whatever but that these planetary and lunar explorations will continue to be of tremendous scientific interest. In order to illustrate for you some of the factors involved in the Mariner 2 experiment, I would like to show you a few lantern slides. And if we can now have the lights out and the slides, please. Stage light up. This first slide is a picture of Pioneer 4, the first space probe launched by the United States to escape from the gravitational field of the Earth, launched in 1959. In order to fix the scale here, the distance from here to the top is about a foot. The weight of this device was about 12 pounds, something you could hold in your hand. The first U.S. space probe to escape from the Earth. The next slide, please. Now, Mariner 2, and to the probe which went to Venus. And again, to fix our ideas on size, about 12 feet from top to bottom, about 450 pounds weight. This picture, without going into detail, will illustrate to you the sorts of construction, the sorts of experiments which are carried aboard. I would like to point out just one or two features of the experiment. The spacecraft flew through space. Let me see if this thing works. Yeah. The spacecraft flew in space with the long axis pointed at the sun. In this configuration, it could collect solar energy on these two panels, which were covered with solar cells, and therefore it could generate electricity to operate the spacecraft. It also flew so that this antenna down here, this circular antenna, was pointed at the Earth. And in this way, communication from the spacecraft back to the Earth could be maintained. And so we have an attitude-stabilized spacecraft pointing at the sun and pointing at the Earth, and kept that way as it traveled on its way to Venus. There were a number of scientific instruments indicated, as you see, which were used during the flight, and I would like to point out particularly the instruments over here, labeled as the radiometer, microwave radiometer, infrared radiometer. These instruments were those which scanned the planet Venus as we went by. The device here oscillated backwards and forwards so that the instruments looked across the planet as we traveled by. Those instruments, incidentally, were turned on by a command sent from the Earth a few hours before it arrived at the planet. The command was sent over a distance of about 35 million miles. It took about 6 minutes for the reply to come back from the spacecraft that says, "Okay, we turned it on." May I have the next slide, please? The path traveled, ranging from, if we imagine this the Sun, the orbit of Venus, the orbit of the Earth. Traveled from here, launching at this time, at which time Venus was here on its orbit, and 109 days later the Earth had traveled to this point, Venus to this point, and the spacecraft had traveled by Venus at a distance of about 20,000 miles. Next slide, please. One of the interesting things which had to be done during the course of the journey was to correct the path of the spacecraft so as to make it go more accurately past the planet. This is to conduct what we call a mid-course maneuver. When we were out about a week from the Earth and about 1.5 million miles, we instructed the spacecraft to perform a maneuver to correct its path. The following things had to happen. First, the antenna, which had been pointing at the Earth, had to be turned up out of the way because we're going to fire up a rocket motor pretty soon. And we didn't want the rocket motor to blast the antenna off the spacecraft. So we turned up the antenna, and then we instructed the spacecraft to roll through a small angle. It turned out to be about 10 degrees. Then we instructed the spacecraft to pitch over, and it turned out to be about 140 degrees. And then we instructed the rocket engine to turn on and run until the speed had changed by about 70 miles an hour. This took about 30 seconds of burning of the rocket engine. So the rocket engine was turned on, turned off, and then after that had been done, the spacecraft was instructed to go back and find the sun, and then come back and find the Earth, and keep that way. A rather interesting maneuver. The commands were sent to the spacecraft from our station here in California. The complete operation took about 4 hours. Next slide, please. The results of this operation were the following. Without the maneuver, we would have passed by the planet Venus at a distance of about 233,000 miles, about the distance from the Earth to the Moon. With the maneuver, we wanted to come within this bullseye. Immediately after we had made the correction, we estimated that we would pass about here. After we had examined the path for about another month and calculated it more precisely, we found that it would come about here. And as we went by the planet, we confirmed that this indeed is what happened, about a 20,000 mile mess. Next slide, please. The communications with the planet are maintained with the spacecraft are maintained by a network of 3 tracking stations. This particular one is the one at Goldstone, California. There are 2 others like this, one in South Africa and one in Australia. Next slide, please. Oh, I'm sorry, that's all, yes. Slide, please. Well, I thought that you might be interested in seeing what some of this equipment actually looks like, and some of the problems we get into in trying to conduct an interplanetary space experiment. Well, now to return to the question of what have we accomplished in space. In the area of technology, the investment has accomplished a number of very important things. First of all, it's given us a much greater insight into the problems of very complex systems. If we're going to conduct such a space experiment, whether it's an astronaut going into orbit or a probe to Venus, we find ourselves dealing with a complex system involving large numbers of people and large amounts of equipment, much of it automatic equipment. The understanding of such complex systems is an important byproduct of the technological developments in space. Similarly, the space program has improved the art of rocketry because of the requirement of conducting rocket firings and parking orbits around the Earth or from space probes which are at a great distance from the Earth. The general techniques of rocketry have been advanced considerably as a result of this program. In the field of communications, the space program has required our ability to communicate over the vast distances of interplanetary space. This is something which would have been utterly inconceivable only a few years ago, and it is really a remarkable achievement. Likewise, space technology has taught us a great deal about the design of instruments, the requirements for operating in space, the requirements of reliability, of limit of weight and volume, of operating in a very difficult environment. All of these things have taught us how to build better instruments, and much of this technology will be applied to other areas. Now, if we look to the future of space, the first and obvious thing, of course, is that we are engaged in an attempt to send a man to the moon and recover him successfully. This is the most difficult engineering task which has ever been attempted by any people anywhere. It will require very large rockets, very complex engineering systems, and be a very expensive undertaking. The nation is committed to this, and as we all know, work is now seriously underway. I assume the Soviets are likewise interested in sending a man to the moon, and I expect they also will be investing the same sorts of resources in this kind of project. But in addition to the lunar program, I think we should remember that there are many other scientific areas of space exploration which will be investigated to an increasing extent as time goes on. The exploration of the planets, for example, is obviously the most fascinating area of scientific investigation. The discovery of life on another planet would be one of the most exciting scientific discoveries of this century. Space applications, of course, will also be exploited. As I said a moment ago, communication satellites, weather satellites, will both be developed to the extent that they will be used as everyday tools in the not too distant future, and undoubtedly new applications will develop as we gain experience in space, some of these undoubtedly in areas not yet dreamed of. Taken as a whole, I must conclude the space program is a continuing dramatic illustration of the advance of technology and science. The program requires the exercise of the utmost ingenuity to solve the technical and other problems. Success in space is therefore a clear demonstration of technological capability of the highest order. We are living in a civilization in which technological capability is an important index of success, and so a successful space program becomes a valued asset of national policy. Hence, we have the US and the USSR each supporting ambitious space programs. Other nations are striving to enter the space arena. Western Europe is actively working on a cooperative project. Many smaller countries are helping in various ways. We are truly entering the space age. I've said that space is a prime illustration of the advancement of technology. In view of concern over the consequences of the development of technology on a broad front, let us examine some of these consequences. Quite obviously, science and technology together are making very rapid changes in our way of life. Nothing like this has ever happened before, although the general ferment of thought associated with the Renaissance made almost as rapid changes in intellectual areas as the present developments have made in our material surroundings. I should therefore like to consider why this rapid scientific growth came about, what is sustaining it, why it happened at this particular time. If we go back to classical times, we find a considerable interest in what we now call the physical sciences and mathematics. In fact, Greek thinkers contributed much of the basic knowledge which we still use. Euclid, with his geometry, established a body of knowledge which is still being used. Aristotle performed an experimental measurement of the radius of the Earth, which was surprisingly near the correct value. Democritus proposed an atomic theory, which sounds very modern in many aspects. Back in Babylonian days, astronomers, or rather astrologers as they were then, had a reasonably good observational familiarity with the heavens, and they were able to predict eclipses. In spite of all this, science did not advance. Perhaps the principal reasons were a lack of appreciation of the universality of scientific truth and of the value of experiment. Many classical scientists were mere catalogers, gathering data from hearsay, drawing doubtful conclusions therefrom. Consider the obvious errors in Pliny's natural history or in the works of Aristotle. Modern science begins with the Renaissance. The spirit of inquiry and of questioning of authority which marks this era extended into the scientific field. Men like Kepler, Copernicus, Galileo began to make careful observations and perform careful experiments. There may be some doubt as to whether Galileo actually dropped 2 different weights off the Leaning Tower of Pisa, but he certainly performed the experiment some way. It's a remarkable thing to realize that because Aristotle said the heavier weight would fall faster than the lighter, no one had performed the simple experiment until Galileo, about 1900 years later, proved him wrong. Newton was born in the year that Galileo died, 1642. With this man, modern science truly begins. His principles of mechanics, his law of gravitation, his experiments in optics, his developments in mathematics, make him the outstanding scientific figure of the 17th century. His work has stood the test of time and still forms the foundation of our engineering, from bridge building to rockets and satellites. The importance of Newton from the standpoint of the development of science is not only that he made some remarkable discoveries, but that he developed a new approach to science, and that other men, his contemporaries and his followers, continued to use his method. Newton's approach can be described as follows. First, the idea of universal physical law. Scientific truth is absolute. The laws of science are everywhere the same. Second, the idea of proceeding from the particular to the general. In other words, the application of the inductive method. Third, the importance of experiment. Scientific truth is subject to experimental verification and can only be determined from careful experiments. Finally, scientific truth requires mathematical analysis for precise understanding and exact statement. Based on these considerations, and particularly emphasizing the necessity for experiment and mathematical analysis, science began to develop very rapidly in a variety of directions. There's no need to attempt to itemize the milestones of progress, except perhaps to note that as Newton developed the science of mechanics, so did Maxwell in the 19th century develop the science of electricity and magnetism. With his great synthesis, the 19th century picture of the physical world appeared to be complete. Only the details remained to be filled out. However, a few years later, experiments began to show discrepancies, and in the early 1900s, two new names must be added to the list. Planck, who laid the foundation of quantum mechanics, and Einstein, who proposed his relativity theory. These two men built onto the laws of Newton and Maxwell the necessary modifications to describe the physics of the atom and of the universe. And so it was in all fields of science. The initial steps taken in the 17th century served to start the rapid growth which has led to our present scientific heritage. The other important area of development is the technological development, which is closely related to the development in science, simply because an understanding of scientific principles points the way for the utilization of these principles. In other words, the scientist is interested in discovering facts about nature. The engineer is interested in using these facts to build something useful. And so by the beginning of the 19th century, we have the beginning of what we call the Industrial Revolution. The first phase of the Industrial Revolution was essentially the application of power, other than human or animal, to operate machinery. Power to operate machinery. At first, this power principally replaced manual labor because it was cheaper and produced more goods. For example, the application of power and the appropriate machinery to the textile industry was the first important advance. However, it was soon realized that power machinery could also do more precise things than even a skilled craftsman, and much of our present-day manufactured goods could not possibly be built without these precision machine tools. Finally, power machinery can do some things which are absolutely impossible with human or animal power. For example, the ability to pack a great deal of energy into a small space has made possible the airplane. This phase of the Industrial Revolution has been responsible for most of the everyday technological devices we see around us. As power sources developed from large, inefficient water or steam engines to small, efficient electrical or internal combustion engines, whole new areas of application developed likewise. Now we're on the verge of widespread application of nuclear power plants. Although these will probably always be large and heavy, the potential of almost unlimited power production with negligible amounts of fuel must inevitably bring about further developments and applications. The next phase of the Industrial Revolution is the cybernetics phase, or the development of automation. Currently, we are in the rapidly developing part of this phase. Automation depends on the fundamental principle of feedback. The machine is asked to compare its output, whatever that may be, against an expected output, and then to stop working when it has reduced the difference to zero. A very familiar and simple example is a thermostat in your house. The furnace stays on until the output, namely the temperature of the room, matches the desired output, namely the setting of the thermostat, and then it turns off. The principle of feedback can be applied in numerous ways and with astonishing results. For example, automatic devices may replace skilled labor just as power machinery replaced unskilled labor. Automatic machinery has been used to run an oil refinery, to operate a power plant, even to operate a subway train. But also, automatic devices can accomplish tasks to a much higher precision in much less time than a human operator. For example, a guided missile, which seeks out its target. Furthermore, automatic devices may operate using sensors which detect radiation, for example, to which a human being is not sensitive. Thus, the control of a nuclear reactor must be done by instruments, which in fact have to work in a region which would be a lethal environment for man. Although we're still in the early phases of this development, it's clear that it will have just as great national and social consequences as the power phase of the Industrial Revolution. The earlier phase initially affected small craftsmen who were replaced by semi-skilled machine operators in large factories. Later, it affected unskilled laborers whose work was done more efficiently by large power machines. The new phase of automation will now replace skilled labor and white-collar workers who've been engaged in simple repetitive work by automatic machines. Presumably, the skills needed to design, operate, and maintain these machines will be of a somewhat higher level, although I might sound an alarming note with the report from the telephone company that they have a central exchange which now runs a test on itself, and if it is in trouble, it rings an alarm and types out an instruction as to the faulty component. You still have to have a human operator who has to read the instructions and then remove and replace the faulty element. However, it's an unpleasant thought to realize that the human operator has become the slave of the machine. I do not believe there is any need to stress the reasons for the rapid growth of technology. Quite simply, it is that machines do more things cheaper and better than manual labor. For example, today, it costs about 5 times as much to dig a ditch by hand as by machine. In more skilled trades, the difference is, of course, much greater, provided only that there is enough work to be done to keep the machine busy. Improvements in machines and the introduction of automation continually decrease the number of man-hours of labor necessary to manufacture goods or to raise and harvest agricultural products. It's estimated that since 1900, the productivity of labor in the United States has increased by a factor of 3. As a specific example, in the General Electric Company, over the years 1956 to 59, production was up 8%, workers decreased 25%. In highly technical industries, developments go through a cycle of research investigations and then a pilot plant and finally complete production of a useful article. This cycle from laboratory to production is becoming shorter with time. It took about 50 years for electricity to come into practical use, and now it seems more like about 10 years from research to production. Thus, transistors were a laboratory curiosity in 1948, and a full-fledged industry a decade later. To quote the example of one industry which is closely allied with technical development, DuPont estimates that half their sales, 75% of their profits, come from products which were in the laboratory 10 years ago. Hence I conclude that modern science, since Newton, has discovered the way to explore and understand the secrets of the universe. Because of the innate curiosity of man, science will continue this investigation. Every answered question raises more to be answered, and the search will never end. Closely allied with this scientific development is a technological development which applies the principles and understandings of pure science. Because of this obvious value in the sense of ability to make useful devices or grow more and better food or control the environment, the technological development will continue to press hard behind the scientists. In a word, the present rapidly expanding technology will continue to expand. Now there are certain aspects of this situation which I should like to discuss. First, the matter of resources. At one time, the most important national resource was good agricultural land. Good land in sufficient amounts would ensure food for the people. Now land is much less important. The efficiency of food production has been greatly raised, and equally important resources are raw materials and power sources. As a matter of fact, even these resources are becoming of less importance. The most important single resource today is highly skilled technical brain power. Highly trained engineers and scientists are necessary if the nation is to keep it standing vis-a-vis other nations. The importance of education in these fields cannot be overestimated. Second, modern technology is able to provide for all reasonable material wants of people all over the world. This is something completely new in the history of mankind. In primitive cultures, the labor of all of the people is needed merely to sustain life. As civilization advances, a portion of the society is supported by the productive labor of the others. This portion may be a governing group, the priests, the soldiers, the rich landowners. Life for most of the members of the society, however, during almost the entire course of history, has been hard and near starvation. Now, however, in principle, technology has shown the way to provide all members of society with a reasonably good life. This is true because we have developed our production, both of food and of material goods, much more rapidly than the population has grown. Technological advances have made this increase in productivity possible. At the present time, there is only a portion of the world in which technology has advanced essentially to this point, however, but in the post-war period, we have clearly seen that nations all over the world are striving to enter into this technological era. Granted that we are living in the midst of an explosive development of science and technology, continuing at an accelerated rate, spreading all over the world, for the obvious reason that it holds the promise of freedom from want, what kind of problems can we foresee? In other words, if technology can satisfy our material needs, why not utopia? Technology is reducing the number of man-hours of production that labor requires to satisfy our needs. And finally, we find that we have surplus labor which may be used in service industries or by the government, both for civilian and military needs, and finally, by an increase in leisure. This increase in leisure, surprisingly enough, I think is perhaps the heart of the problem. How can we educate people to be able to use their leisure in a constructive fashion? By what standards shall we judge whether this leisure is well spent? Western civilization has strongly emphasized the importance of labor and also of thrift, but an economy of plenty wants neither. How do we readjust our standards? For man to live a happy and useful life, he must feel in tune with his environment and his fellow man. He must feel that his motivations and ideals are supported by his fellows, otherwise he is an outcast. Because of the rapid evolution of our technological society, much of our social culture has not been able to keep up and is better adapted to an earlier time. we have the basic difficulty that is simply expressed by a yearning to the good old days. This is really an admission that the technical world is moving too fast for us. In some cases, this may lead to serious emotional disturbance or a refusal to face the realities of the modern world. If we look to the future, it would appear that we must learn to evolve our cultural and moral standards more rapidly than in the past, or else find an increasing discontent with a potential utopia. In a word, the problem which must be solved can be stated thus: given a growing technology and its ability to provide us with all of our material needs, how can man learn to live with himself and with his fellow man? I've posed some problems. Now I would like to consider some of the decisions which face humanity as a result of our developments in science and technology. The rate of evolution is increasing and far outdistancing our social and biological evolution. It cannot be stopped. It may slow down as other aspects of our civilization exert counter pressures. It may reach a plateau. In fact, it certainly must reach a plateau sometime, but that time does not appear to be in the immediate future. Therefore, let us examine the sorts of decisions which science has made inevitable. First, and most important, is the decision as to whether we want to commit race suicide. Science has given us the tools to do so. We could probably do it tomorrow. We can certainly do it a few years from now. It's not a subject to be dismissed as too improbable or too unthinkable. Even in the animal world, some strange things happen to social groups. For example, the lemmings of Scandinavia are reported to march into the sea and drown in enormous numbers for no apparent reason except possibly the pressure of population. Likewise, in human history, some very strange things seem to happen under the pressure of motivations which appear quite incomprehensible a few years later. An example is the Children's Crusade of the Middle Ages, or even the trench warfare of World War I. Neither accomplished any useful purpose. Of course, the whole history of warfare is filled with examples of useless fighting for irrational purposes prolonged far beyond any conceivable value. So we must conclude that man is subject to irrational urges to violent action, and that mass suicide is not out of the question. Since the power to unleash full-scale nuclear warfare is in the hands of a very few individuals, since a decision can be reached in a matter of seconds, it might seem to be almost impossible to provide such an assurance that such a decision will not be made. In fact, the situation is potentially even worse because of an increasing tendency to rely very heavily on computers and radars and such to make the key decision, which leads to the danger of an electronic failure releasing a holocaust. The recent bestseller, Failuresafe, presents one such possibility very dramatically. It's not yet clear how we can reach the decision to make race suicide impossible, but it is clear that there must be an increasing awareness of the necessity for such a decision and a continuing search for the answer. If we do not find a decision, a solution, we are voting no by default, and the human race will be fortunate to see the year 2000. Let us assume that I am too pessimistic and that either the situation is not as fraught with danger as I indicate, or else that a real solution is found. What then? A second vital decision area will face us when the biological sciences have attained the same kind of understanding of the living world that the physical sciences have attained of the inanimate world. Understanding will bring with it the ability to modify or control. Just as we are increasingly faced with the consequences of this ability in the physical world, so too, in a manner which will be of far more direct concern to individuals as human beings, will we have to face some very fundamental issues in the biological world. Some of these problems are already upon us. For example, medicine is able to do some remarkable things as a result of understanding disease and the chemical and physical actions of the human body. But as a result, there is an increasing number of people who are kept alive but who find great difficulty in living normal, happy and useful lives. The fundamental precept of medicine has always been to save life at any cost. As we become more skillful, we are able to keep a spark of life in the very old or the very sick, even though they may be living only a sort of vegetable existence. In the future, this will be more true. Therefore, the question of the ethical position which a doctor should take towards euthanasia is one byproduct of the development of medicine. Other examples of ethical decisions which have already arisen as a result of advances in biological sciences include such matters as our attitudes towards birth control and truth serums. If we look into the future a little way, we can see some remarkable possibilities with psychological drugs, and in the genetic area with controls comparable to what has already been accomplished with domestic animals. Clearly, biological science will require an acceptance and understanding of the extent to which the scientist can be permitted to play at being God with the human body and the human mind. Again, if the decision is not made, we might someday face the misuse of science to an extent as devastating in its effects as the potential of nuclear bombs. The third area of decision-making concerns the authority and responsibility of science. Within recent years, the scientist has been given more financial and political authority than he has ever before enjoyed. The estimated expenditures of the federal government for research and development will reach $15 billion in the next fiscal year. In addition, private expenditures may reach $5 billion more. Comparable figures for 1940 are 100 and 300 million. Even in 1954, the figures were only 1 and 2.5 billion. Although most of this money is spent on applied science or developmental engineering, nevertheless, science has control over very large resources. Likewise, in a political sense, government is increasingly aware of the necessity of inviting scientists into the inner circles of government policy, not only to help understand the significance and utility of the sums of money being spent on research and development, but also because science per se has become an important instrument of national policy. Consequently, scientists, as responsible citizens, have a clear responsibility to conduct their research for the government to the best of their abilities and to be financially responsible in their expenditures of public monies. Likewise, they have a responsibility to advise the government on matters in which they are competent. Scientists are like the rest of us. There are good ones and bad ones. But I have every confidence that in these matters of relations with the government, scientists are indeed responsible. I am concerned, however, about another phase of scientific responsibility. As the resources and powers available to science increase, the possibility of performing experiments which have far-reaching or even irreversible effects on our environment increases. At one time, some people were concerned that nuclear experiments might blow up the whole Earth. This, of course, is a groundless concern, but the problem of nuclear fallout is not. Fortunately, the scientists involved have indeed been responsible and no serious harm has resulted. There are other experiments, however, with more subtle results. For example, the widespread use of DDT in some areas has caused a significant change in the balance of wildlife in those areas. The recent very high altitude nuclear explosion has significantly changed the innermost Van Allen radiation belt. Probably no experiment has yet resulted in any very harmful, unexpected result, but with increasing capabilities, the possibilities must increase. Any such experiment, therefore, whether it be weather control or insect elimination, should not be performed without a public understanding of the consequences. The decisions which have to be made relative to the extent to which the public is willing to allow the scientists to experiment with the environment. I do not believe the consequences of allowing this decision to go by default would be very harmful, because I have a great deal of confidence that scientists will not perform an experiment of this sort without proper analysis. But I do think it is a matter for public debate and understanding if relations between certain scientific groups and the public at large are not to be unduly strained. Finally, a fourth area where vital understanding and decisions are needed is the broad area of understanding how to live in a world which is capable of a technology of plenty. Even though it's possible to produce ample food and material goods, we have not solved the problem of distribution or the problem of developing a successful mode of life for large portions of humanity. In a biological, evolutionary sense, very little separates modern man from Stone Age man. Occasionally, in fact, the more primitive aspects of humanity break out in strange fashions. Consider Nazi Germany in the immediate pre-war years, for example. Actually, of course, we live in a world which contains a very wide variety of social cultures down to the very primitive. With every year, modern communications are bringing the world ever closer together, so that on the one hand, we have very advanced technological civilizations, on the other hand, only a few hours away, the most primitive social groups barely able to sustain life by crude agriculture or hunting. Therefore, it's necessary to develop an understanding of the proper relationships which should exist between various social cultures. Decisions must be made as to how to implement these relationships. In the early days of this country, many problems were caused by giving alcohol and firearms to the Indians. Whether this was good or bad is not the point. But translating this situation into the conditions of today, we must understand what are the consequences of disturbing a primitive social culture by suddenly adding some of the gadgets of modern technology. During the last few minutes, I've been raising various problems and related decisions which are a consequence of modern science. Now, in conclusion, I'd like to sum up some personal views. I started by asking if we were headed for a negative utopia founded on a scientific dictatorship. I will say probably not. One reason, science and technology are moving away from the rigid mechanistic determinism of the late 19th century. At the end of that century, the pattern of physics was represented by the mathematical laws of Newton and Maxwell. All actions were the result of applied forces, and given the forces, the actions could be exactly calculated. In other words, if we know the exact condition of every atom in the universe at a certain instant of time, we could, in principle, compute exactly what would happen at all future times. Along with this determinism was a belief that all the basic laws of the physical world were understood. It seems to me that the orderly scientific dictatorships of Bellamy and H.G. Wells are a consequence of this orderly, mechanical, physical world. Science today, however, not only knows a great deal more about the physical world, but also has a much more humble attitude towards its knowledge and its lack of knowledge. Furthermore, science has found that at the atomic level, the certainty of Newtonian mechanics disappears into the probability functions of quantum mechanics. And on the very large scale of the astronomical universe, Newtonian mechanics must be replaced with the laws of Einstein. In both cases, the very small and the very big, the behavior of the physical world does not obey the dicta of common sense. Coupled with these developments in science are developments in technology which carry us further into the realm of cybernetics. The more we make machines automatic, the more we can make them responsive to individuals. Thus, many buildings today have room temperature control which you can adjust to suit yourself. The modern automobile with power steering and automatic shifting and all the rest does not require a trained engineer to drive it. The modern telephone allows you to talk to your friend anywhere without invoking messenger boys or switchboard operators. So it appears to me that science and technology together are moving into an area where the individual is becoming increasingly important. He's no longer a cog in a vast machine, and therefore hopefully we are moving away from the threat of scientific dictatorship. We are living in one of the golden ages of history. Never before have so many people been able to live the good life. But regardless of whether there is a scientific dictatorship or not, there is still no guarantee that this golden age will last. First of all, there is our need to keep our present physical powers within bounds and to assure that our future biological knowledge and power is kept under control. There is a need to keep our productivity ahead of our population. and to develop satisfactory means for incorporating modern technology into less advanced cultures. Finally, there is a necessity that the cultural evolution of our society should be able to find new ethics, new motivations, new principles appropriate to the dynamics of material and technological developments. One final thought. Civilization has always seemed to require a governing elite and slaves to provide the elite with food, shelter, clothing, and all the other material appurtenances of life. Since the Industrial Revolution, the slaves have been machines. Now the machine is acquiring judgment and perhaps a little intelligence. Our material civilization is so successful because we have so many machines working for us. In the past, many civilizations have fallen because of a revolt of the slaves. Will we ever have to face that problem with our machines?
Very deeply indebted to Dr. Pickering for these thoughtful and provocative, and I was going to say frightening, even hair-raising comments in consideration of some of the more depressing of Dr. Pickering's observations. It becomes perfectly clear why man should wish to probe into space. It's to get away from the Earth, obviously, and these problems. In any case, I'd be very much surprised if Dr. Pickering's comments had not raised in your mind a number of questions which you might wish to take up with him. And since he's agreed to expose himself to your questions, and since further he's very much a man in motion, you know, he's off to New York and Washington and Venus and other parts all the time, this is, I think, a rare opportunity, and I would urge you to take advantage of it and to raise with him any questions that you might have for a few minutes now. Once again, Dr. Pickering. If there are questions.
Yes.
What are the state of efforts to pick up communication from other planets? This, of course, is not as militarily necessary right now, but I understand there are considerable efforts being made.
Let's not say other planets, let's say
Outer space.
from outer space, yes. Yes, indeed, there are some efforts being made. In fact, if I may quote one of my astronomer friends, he has tried to make an estimate of how many places in the universe in our local galaxy now, let's at least limit ourselves to our galaxy, and how many places within our galaxy could we expect to find planets with conditions not too different from what we find on the Earth. And after going through some numerical exercises which involve a certain amount of astrology, I suppose, he comes up with a number like 100,000. And so then he says, now if there are possibly 100,000 planets with conditions similar to ours, let's assume that life has developed on these. It is unlikely that life would have developed in exactly the same time scale on all of these. And if you recognize the long history of evolution of life on the Earth, you realize that what has happened in the last 300 years, the whole development of science from Newton to space probes, has occupied an infinitesimal segment of time compared to the development of life. And therefore one would expect that in other comparable situations, one could find perhaps civilizations which were many thousands of years ahead of our own. And so one asks the question, if they're many thousands of years ahead, would they be interested in such things as exploration of the universe? And perhaps they would be, or perhaps they would have gained enough intelligence to have decided not to explore the universe. So if they did explore the universe, then we might expect an attempt to communicate with other elements of the universe, or perhaps even to travel to other segments of the galaxy. And in fact, This is not an unthinkable situation that one could perhaps travel to another star someday. And so he looked for two things. One, evidence for communication, and another evidence that they have visited us. Now, the evidence that they have visited us, of course, poses another interesting problem, because as he says, supposing you did explore another solar system and you found a planet there and it looked interesting, and you wanted to put some sort of a marker on it so that you would know that you'd been there before, you know, go away with you. And also so that you would remember which one it was when you wanted to come back some other time. So what would you do? And the answer is you would not put it on the planet, because if you put it on the planet, the very fact that it's interesting probably means there are people on it, and if there are people on it, this marker will be destroyed. And so what you do is put your marker into orbit around the sun, alongside this planet somewhere. So he suggests that we should look for artifacts in orbit around the sun. And it poses an interesting question as to how to do this. But also, though, it does, seriously does pose the question in a number of people's minds as to whether we shouldn't be looking for communication with other planets. And a few people are doing this in the sense of listening with radio signals. Then, of course, the next question is what kind of a signal should you expect to receive? And there have been various hypotheses that if you wanted to communicate with another intelligent civilization, you would start out by performing some simple exercises in arithmetic and see if they responded. And so people have been looking for these so far without success.
Could you expand somewhat your ideas on problems associated with the utilization of truth serum?
I just raised it as an ethical problem. Just as the point I was really trying to make was that to a certain extent the biological sciences are now in about the stage that the physical sciences were in the early 1900s. And in the next few decades we can expect some tremendous developments in biological sciences. These developments will, I'm sure, pose